Hello students, welcome back. We have been doing some linear models. We went through a couple of application problems. One about average rate of change, linear model or not. The other, working with two linear models at the same time. We end up with setting these two equal to each other for equilibrium, the solution, and the function value at this solution. And then inequality, those kind of things. All right, next, what do we have here for piecewise linear models? This problem's a bit too much of a textbook example. Okay, sometimes we have rate of change stays constant in a certain interval, but we have different rate of changes for different intervals. Let's see, yeah, like this. When x is less than -2, we have one linear model, blue, with slope 2. And in the second interval, between -2 and +3, we have slope 1. And then x is greater than 3, we have slope 1/3. And this kind of linear model. And most of the time, you're going to end up with continuous model because we are dealing with most of the real-life application problems. But do not just worship the continuity. Sometimes you don't have those kind of things. For example, if you go over to stock market and then check out those stock prices, for example, and you see some big discontinuity, big jump one way or the other around the earnings announcements or something like those. So discontinuities do take place. Here we are doing 1000 level course, so most of the time things are continuous. That's about it. All right, so much for theory on piecewise linear models. How about some real problem here? Okay, here we go. Two 2018 tax return schedules are presented as below. Let x be the taxable income and express the tax due as a function of x. And then one schedule is for single and the other schedule is for married filing jointly or qualified widow or widower. Okay, all right. Let x be the taxable income and express the tax due based upon schedule x. So look at this one for part A. And part B is this one. And then part C, you have to answer some question. Okay, how about part A? Well, depend upon your x value, the income, between 0 and 9,525, we have one linear function. 0 plus 10%, 0.1x, right? So 0x then tax money that you have to pay is going to be 0 plus 0.1x. That's what you get from the first line. Make sense? The interval is explicitly here, and then you have to read this in order to figure out the tax for that. Next. 9. Oh, wait a minute. What am I doing? This should be 0. It should be 0. It was typo. 9525. And then the next one is 38,700. Okay, is that clear? Now, what do we have here? Not 0 plus, but 952 plus, and then now 12%. But then again, this is not going to be 12x. what do we have here? Is it going to be 12x or something else? Of the excess over. So income above this 9,525. So this is x minus 9,525. As a matter of fact, over here should be this is x minus 0. So up to 9,525, you pay based upon 10% tax bracket. And then if you made, say, 10,000, then $475 will be subject to 12% tax bracket. Make sense? Not the entire $10,000 is 12% bracket. So up to 10%, you're paying this much, and then above that, you're paying based upon the tax ratio of 12%. Let's do just one more time. 38,700, and then up to here. Is that clear? 82,500. Yeah. And then what's my tax? Now 4,453.5 plus. And then what's the tax bracket? 22%. But not the entire 80,000, not the entire 50,000, but excess over 38,700. You see, first 9,525 is taxed based on 10%, and then after that, up to 38,700, 12%, and any excess of that will be taxed by 22%. For example, if you make 40,000, then 40,000 minus 38,700, so that is 1,300 will be taxed in 22%. Not the entire 40%, okay? And then you'll have to continue and then get all those intervals. Make sense? Let's see, what do we have in my answer key? Oh yeah, all these. And then here I used if part, the interval part on the right hand side. Here I put if part, interval part in the left hand side, but that's the same thing. And then instead of T for tax, I'm using F. And as for these expressions, they're all the same. I'll just use this one. And if you do the same thing for this, you're going to get the answer for the second problem. So 10%, 12%, 22%, 24%, those tax rates are the same, but the intervals, tax brackets are different. Now that you have two functions, you can actually plug in. For example, if the husband had taxable income of 35,000 and wife had 40,000, what is the household's tax if they follow X, married filing separately, that is $35,000 here, 40,000 here, and then add them up, versus using this table, married filing jointly, so add them up, $75,000 based upon this. So whether you use F for 35,000 and 40,000 and adding them up versus G, all 75,000 and working out. Just do your computation and then you can compare. It turns out you pay more if you file tax separately. Yeah, that's usual. I mean, married filing jointly is better. That's supposed to be better as a matter of fact. But there may be some exceptions. For example, if husband is actually, for example, foreign national, and then there's some foreign tax credit and so on and so forth, in that case, one of them may become much smaller if filed separately. Things like those happen, as a matter of fact, but rare. Anyway, here's an example of piecewise linear model, and it'll turn out these are all piecewise, but they'll turn out to be continuous, just different slopes, different average rates of changes. Let's see, enough time for these examples. Linear regression. I don't want to go too deeply into this. Instead, I'll just show you some pictures to show you how you actually use linear models in real-life situation. Let's see. Monthly averages of daily high temperatures are mostly positively correlated within the continental United States. And we ended up with this scatter plots based upon NOAA data. And this is correlation scatter plot for monthly average of daily high temperatures of Dallas and New York from 1914 to 2020. Now, these are not daily, but monthly averages. So if you have daily temperatures, then they're going to vary a lot more, so you're going to get a lot weaker correlation. Anyway, in this case, correlation is pretty strong, 0.959 something, and line of best fit looks like this. And then based upon this line, you can do some prediction. These kind of things are called regression, and that's going to be important in statistics. In STEM algebra, there's some problems associated to doing these kind of problems using technology. In business algebra, it's going to be even more important here because all those business we do are related heavily toward approximations coming from real data. So this should be emphasized even more in business algebra if you just look at it in business point of view. But as far as in 1000 level is concerned, our textbook is not putting much emphasis on it. And that's why I'm not assigning any problems. I'm just showing you these pictures to show you that how people utilize these kind of things. And then in order to get those, and then sometimes using these correlations, you get some interpolation using piece by piece, and then those are related to big data and machine learning and things like those. So we are talking about something highly applicational in business world as well. And this one, even though this came from weather data, because weather data are free, and then I just get those myself and then created a program myself, so that I don't have to pay for any kind of copyrights or anything like that. And that's why I took the weather data, which is available for free. But if you use business data, then more directly applicable in business world, except that the data set will not be free. Anyway, Dallas and New York, and Dallas and Los Angeles. And as you can see, correlation is a bit weaker, but still you can see some linear correlation, so you can set up a linear model. Dallas and San Francisco, even weaker. Dallas and Honolulu, even weaker. And I wanted to check negative correlation, so I took Dallas and American Samoa, which is US territory in Southern Hemisphere. So as it gets hotter in Dallas, it actually gets cooler there because it's an opposite hemisphere. And those kind of linear models are the kind of thing that people will have to study eventually and seriously when they are going to do business algebra. But for now, it was just a good preview. After all, this is just 1000 level course.